Hello, young lovelies. We're going to learn a little bit about the cardiac cycle today. Now that you know what some of the chambers are called and some of the structures of the heart, now we're going to learn exactly what happens inside the heart. So a cardiac cycle is considered one complete heartbeat. The contraction of the heart chamber is called systole, and the relaxation of the chamber is called diastole. So, contracting of the heart, systole, relaxation of the heart, diastole. Because it says here, okay. So, hold on. Jesus. Right here. Export. Wait, it's already saved. What is going on? Oh, you just click that. I think it's actually you want to overwrite that. So systolic blood pressure occurs when the blood is forced out of the left ventricle and the aortic valve remains closed. So that should be closed. And that's the high number on a blood pressure reading. Diastolic blood pressure occurs when the aortic valve opens. And that's when the ventricle relaxes. So think about it. When it opens up, the ventricle can relax because the blood's flowing through. That's the lower number of the blood pressure reading. So the average blood pressure is 120/80. The average heart rate is 70 beats per minute. Now this is obviously, kind of iffy for everybody. That's just a normal reading. However, typically when this number, this top number, the systolic, becomes over 140, then we start asking ourselves some questions like that's a bit high. When this bottom number over here is over 100, we start to say, that might be a little high. And the average heart rate, I'd say resting, this is resting, so not when you're exercising, but when you're resting, is around 70 beats per minute. However, we don't really start getting concerned until your resting heart rate is probably around 90 beats per minute. That's a bit high. So again, average blood pressure for an adult is 120/80. Again, varies by person. You have to kind of figure out what's normal for you. So sometimes people, if they think they're having blood pressure issues, they will take their blood pressure with something called a sphygmomanometer. So you can see on the bottom there, it's sphygmomanometer. 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 So I know you're all repeating that to yourself right now. Sphygmomanometer. Probably one of my favorite words in science, sphygmomanometer. But we're going to do a lab where you learn to use a sphygmomanometer and to check your blood pressure. It's kind of a skill. It takes a while to learn, so it's pretty tough at the beginning, but we're going to give it a try soon here. So what blood pressure actually is the force of the blood against the walls of the artery. So when we do the blood pressure, we record it as two numbers, the systolic pressure, which is the top, so we record it as a fraction, again, 120, over the diastolic pressure, so an average of 80. So this is when the heartbeat is contracted, this is when it's relaxed. So this is the systolic, and this is the diastolic blood pressure. So the cusps or the flaps of the bicuspid and tricuspid valves are anchored to the ventricle walls by these cords called the chordae tendineae, which are attached to the wall by papillary muscles. This prevents the valves from being pushed up into the atria. So these things basically secure them down. So first, let's identify bicuspid and tricuspid. We can see tricuspid would be number 2 right here, and bicuspid would be number 5. And so what happens then, if we look a little bit closer, we can see that the papillary muscles are going to be these ones right here, number 7, and then the chordae tendineae, they look like cords, that's number 8. So again, we have the papillary muscles, and then the cords, and then the valve up here. Okay, so you've probably heard of an EKG or ECG, which is considered an electrocardiogram. This is a recording of the electrical events during a cardiac cycle. So obviously the body is run on a huge electrical current. So there's lots of different things we can look at when looking at an EKG. One of them is considered the P wave. This is the depolarization of the atria. So this is when the atria contract. That's considered systole. So that's the P wave right here. And then there's what we call the QRS complex. And this is the depolarization of the ventricles. So this is when the ventricles contract and are in systole. So that's the QRS complex. This one right here in the middle, QRS complex. And then the T wave is the repolarization of the ventricles here at the end. We definitely look at this QRS complex as a major indicator of some problems happening right here because that's the ventricular contraction. And as we know, when the ventricles contract, that's when the blood goes out to the lungs, and that's when the blood goes out to the body, which is like the super important part. So if something's messed up with that, then we got major problems happening within the body. Now, the sounds that you hear, that kind of like lub-dub sound, is really when it's the valves opening and closing. So the flow of blood into and out of the chambers, kind of the vibrations in the muscle, all those things are what you're hearing, that lub-dub sound. Like I said before, again, opening and closing of the valves. We use a stethoscope. That is the instrument that we use to listen and measure the heart sounds. There are some different things that you can check out. Maybe after you get off this PowerPoint and after you're done listening, maybe try to Google some of the different sounds of the heart. So just kind of Google different sounds of the heart, like murmurs or mitral regurgitation or stenosis, or just a normal heart sound, and see what that sounds like. Okay, so how does the heart conduct itself? Well, there's this thing called, there's a few things that are like super important. First is this SA node found in the right atrium. And then these, the AV node is another one right here that is a major player. And then we have this AV bundle. This bundle is kind of in the middle here. All kind of play a major role in the electrical activity of the heart. So not so much the functionality like valves opening and closing, but it's the big electrical component to the heart is run by these things. So this is just kind of a picture like showing how the electrical current of the heart happened. We use these things called Purkinje fibers to kind of help with the electrical current. I mean, just think about just how the electricity runs in your house, right? There's a bunch of, wires and things. I'll be honest, I'm not an electrician. I don't know everything about that, but I do know that there are some electrical wiring, and somebody has to come in to wire your house in order to have electricity. So it's kind of the same way within your heart. There have to be these different wires that come from one source. So like you have your electrical box, and then there's wires that come from it. So that's kind of like the SA node is the box, and then all these little fibers kind of come off of it to deliver the electrical current. So again, go back and look at your notes to kind of figure out if you can figure out what the SA node is, what the AV node is, and the Purkinje fibers, and locate them through here. Okay, hopefully you did that and you found all that, you figured out what number 1, number 2, 3, 4, and 5 are. Okay, this is on the, you can kind of look at some of these heart animations on McGraw-Hill, which is your textbook website. So if you want to kind of look at that after this as well, if you go to my website, I have the textbook website on there, and you can go to the conducting system of the heart to check that out as well. Okay, so regulation of the cardiac cycle. obviously, the brain is in charge of everything. So the cardiac center is located within the medulla oblongata. That cardiac center is what signals the heart to increase or decrease its rate according to the many factors that the brain monitors. So, muscle activity. If you're exercising and your muscles need more oxygen, that medulla oblongata is going to trigger the heart to increase its beating so that your muscles get more oxygen. Same thing with blood temperature, same thing with levels of potassium and calcium. Sometimes the heart has to increase its rate or decrease its rate because of something that that's happening inside the body. And what tells it to do that is the cardiac center within the brain, which is more specifically located within the medulla oblongata. Okay, so your cardiac volume is your stroke volume times your heart rate. Okay, now what does that mean? That means stroke volume is how much blood is coming out in one contraction. And then obviously your heart rate is how many beats per minute. Again, this is just kind of a picture showing you some of the more, just take time to take a look at it to see if you can understand the parts. We're obviously going to be seeing all of these in person on the sheep heart right in front of you, but it's good to start on a diagram. Okay, so some issues that can happen with the heart is I'm sure that some people you've heard of SIDS in infants, sudden infant death syndrome, but there's something also called SADS, sudden arrhythmia death syndrome, or sudden adult death syndrome. And what happens is this is where you hear sometimes of the high school kids, you know, they were playing football and all of a sudden something happened to them. This could be because of a sudden arrhythmia death syndrome. That's why you see a lot of maybe perhaps high school physicals requiring ECG screening, or if there's anything that doctor during your high school like sports physical detects, like a murmur or anything, they're automatically going to send you for an ECG just because of SADS. So how do we interpret the ECG? Well, first, an ECG is printed on paper, and it's covered with a bunch of grids of squares. So you can notice that there's 5 small squares on the paper, and that forms a larger square. The width of a single small square on the ECG paper is 0.04 seconds. So a common length of an ECG printout is 6 seconds. This is known as a 6-second strip. So you can see right here that the little box right there, that's 0.04 seconds. So a long strip right here would be just 6 seconds of your heart. Okay, so looking at the ECG, we can see that obviously we talked about the P wave. Now this is super interesting. So the P wave right here is right here. That's when the atria contracts, right? So activation of the atria. The QRS complex is the activation of the ventricles. And then the T wave is recovering. So how is the heart recovering at the end? So if we look at these things right here, we see this is a normal heartbeat. Okay, we can see like you can look at how many squares are in between kind of these little peaks right here. You can see that that's pretty normal. Now if we look, this is what we call tachycardia, which is a fast heartbeat. So you can see that there's less time in between each of these little peaks right here. Less time, less time, less time. And then here's a slow, this is what slow heartbeat, we call it bradycardia. So look at all the time in between here, that's very slow. And then here's an irregular heartbeat. See how it's not consistent? It's kind of like fast, slow, normal, 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 slow. You know, it's irregular. So how they do that, the ECG is they simply put a bunch of leads on you as a person, like they did on this guy. So you get a bunch of leads on you and you just sit there. So the person doesn't have to do anything. You don't have to go through anything. They just put a bunch of leads on you. It leads into a machine and then prints out that printout so that we can take a look.